Some polynomial theorems. First one is known as the remainder theorem. And it simply says, well, if you're going to divide by a linear factor, then all you've got to do is substitute the number in, so it's x minus something, and whatever you get, that's going to be the remainder. Here's a proof of that. Remember we said all polynomials can be written as divisor times quotient plus remainder. Okay, so let's say the divisor is x minus a. So let's rewrite it. So now polynomial x minus a times the quotient plus the remainder. Now if I substitute in a, we're saying the answer should be the remainder. Sub in a and I get a minus a qa, well a minus a is 0. So I know polynomial a is equal to remainder a. But the thing I know about remainder a, if I'm dividing by a linear function, the remainder must be of smaller degree. And the only thing smaller than a linear function is a constant. So remainder a, remainder x, it doesn't matter what I substitute into the remainder function, I'm always going to get the same answer. It's going to be a constant. So polynomial a does indeed equal remainder x. So there's a quick little proof of that one. Let's use it. Rather than doing the whole long division, but sub in 2 to find out what the remainder is, we can save ourselves a lot of time. Don't actually have to do the division, just sub in 2, and there we go, straight away, negative 19. I know the remainder will be negative 19. This makes a more useful theorem, the factor theorem, because the simple idea is, if the remainder is 0, then I know it's a factor, because there's no remainder. So it basically is the remainder theorem, but what we're saying is, if the answer, that remainder, turns out to be 0, then I know it factorises exactly with that one. And that is very useful when we're trying to, obviously, factorise polynomials. So here we are, x minus 2. First of all, we're going to show it as a factor, and hence go and factorise the actual polynomial. So I can sub it in. Yes, I get an answer of 0. So I know x minus 2 is a factor. The question is, what is the other factor? This is a silly thing to do, which I'm about to do. Because if I was going to do polynomial division anyway, I wouldn't have worried about the factor theorem, because if I'm going to do polynomial division, I'll end up with no remainder. But this is how I would find the other factor, maybe. So x into x cubed is x squared. Let's keep going. That brings up 2x squared. X into 2x squared, 2x. Keep going. X into minus 15x is minus 15. And sure enough, a remainder of 0. So that would be another way of showing there is a remainder of 0. So I know polynomial x is x minus 2, x squared plus 2x minus 15. But that second quadratic also factorises. And it's plus 5 minus 3. So you might be thinking to yourself, well, what's the point of the factor theorem? I had to go and do polynomial division anyway. In reality, I probably wouldn't have done that division. This is what I would have done. There's my polynomial. We just showed x minus 2 is a factor. So I know x minus 2 is a factor. It's going to be x minus 2 times something. And basically we just work it out by a little bit of logic and common sense. Now, I know the leading term times the leading term would end up with the leading term. So x times something is going to give me x cubed. Therefore, x squared. I can do the same with the constant. The constant times the constant must give the constant. So minus 2 times something is going to give me 30. That'll be negative 15. How many x's are going to be in there? Well, if I was just to leave it like this and expand it out, I would have minus 15x. I want minus 19x. So therefore, I need another minus 4x. So minus 2 times what would give me minus 4x? Minus 2x. So that must be the middle term. So that's the basic thought process you go. You go, well, look, if I was to expand out now, how many x would I have? And so that answer is minus 15x. How many do I actually need? Well, I need minus 19x. So how do you get from what you have to what you need? We needed another minus 4x. And then we went, minus 4x times minus 2. Minus 2 times, 2x. Okay? So I don't have to do that whole long division process. And then we factorise the second one and come up with the same answer. Let's try another. 4x cubed minus 16x squared minus 9x plus 36. They haven't given me a hint this time. They haven't said, show that this is a factor. All polynomials can be factorised to be a combination of quadratic and linear functions. Okay? This is a cubic. Therefore, there must be a linear factor. Because if there were only quadratic factors, then the order of the polynomial would have to be even. Because you'd have x squared times x squared times x squared times however many x squared. You'd always end up with an even number. So there must be at least one linear factor. So I can use my factor theorem. I just need to pick random numbers and hopefully I get the answer 0. In reality is I don't just pick random numbers, I use common sense. Remember what we said? Constant times the constant equals the constant. I know it's going to end up 36. So the logical numbers to pick are factors of 36. So if they're going to be factors, there they are. I could have 1, 2, 3, 4. I deliberately picked a number there that had a lot of factors. 6, 9, 12, 18, 36. They're all possibilities that I could try. But they could be negative as well. So we've got -1, -2, -3, -4, -6, -9, -12, -18, and negative 36. But because it's not monic, when I factorise it, it might not be x minus something. It might be 2x minus something, in which case the answer would be something over 2. So all the ones that have that sort of form, that fraction, would be factors of the constant divided by factors of the leading coefficient. And again, I've deliberately picked something that has a couple. So we could also have 1 quarter, 2 quarters, 3 quarters, 4 quarters, 6 quarters, 9 quarters, 12 quarters, 18 quarters, 36 quarters. Mind you, a couple of those are whole numbers and we've already got them in our list. But 2 also goes into 4. So I could have 1 over 2, 2 over 2, 3 over 2, 4 over 2, 6 over 2, 9 over 2, 12 over 2, 18 over 2, 36 over 2. But again, some of those we already have in our list. So let's just cross out the doubles. There's all our possibilities. But remember, they could also be negative. So we need to pick a logical one to substitute in. What is the most obvious one to try first? 1 is going to be the easiest number to substitute in. And if we're lucky, it works. If 1 doesn't work, we'll probably try -1. But by the way, if 1 does not work, I'm not going to try 36. Because it would have to factor, you know what I mean? So 36 is not going to be. So we can narrow it down a couple of ways like that. So like I said, the logical one to pick first is 4. I just picked 4. So let's see. Oh, how lucky did I get? Look at that. Hey? 4 happened to work. So we know x minus 4 is a factor. Let's go factorise. Okay. Leading term times the leading term must give the leading term. X times something gives me 4x cubed, 4x squared. Constant times the constant gives me the constant. Minus 4 times something gives me positive 36 minus 9. All right. Well, how many x do I have at this stage if I was to expand out? It's not a trick question. Anybody feel free to answer. Minus 9x. How many do we need? Minus 9x. Oh, we got them all. That must be it then. Now, if you're looking at that thinking, oh, hang on, that sounds a bit suspect. Don't quite believe that. Well, there's another term we could check. Let's check the x squareds. If I was to expand this out, how many x squared would I have? Minus 16. How many do I need? Minus 16. So there you go. But of course, that second one does factorise. Telling me those, by the way, if you hadn't have picked 4, the other ones that would have worked would have been minus 3 on 2 and plus 3 on 2. Might have taken a while to pick that one randomly out of that list, but they would be the other ones that worked. 2004 HSC. Right. So here's our polynomial. They've written it a rather funny way, but there it is. They've told me that when it's divided by x plus 1, the remainder is negative 11. Divided by x minus 3, the remainder is 1. What's the value of b? Okay. I know polynomial negative 1 is negative 11. Because when I substitute in negative 1, I would get the remainder. So substituting that in, oh, actually it comes out quite nicely, doesn't it? Because when I sub in negative 1, that all disappears. The ax plus 1 disappears. B equals minus 11. Very quick. What's the remainder when it's divided by x plus 1, x minus 3? Well, now we're going to have to find a. Because if you look at how it's set up, the remainder is ax plus 1 plus b. Because over here, it's multiplied by x plus 1, x minus 3. So if I can find a, let's use the other piece of information. Polynomial 3 is equal to 1. So sub that one in, we get 4a plus b is 1. We've worked out b is negative 11. So a is 3. My remainder, therefore, is 3 outside of x plus 1 minus 11, which works out to be 3x minus 8. 2002. So x cubed minus 2x squared plus a is going to factorise to be x plus 2 qx plus 3. Qx is some polynomial. Find the value of a. Ugh. What should we substitute in? There's a logical number here to substitute in. Minus 2. Because look on the right-hand side. We don't know what qx is. But if I substitute in minus 2, it'll disappear anyway. So I'll be able to get an answer. Sub in minus 2, and the answer is going to be 3. So, okay, minus 2 cubed, minus 2. A is, there it is, 19 for that one, 19. 1994. When the polynomial is divided by x plus 1, x minus 4, the quotient is qx, the remainder is rx. Why? Now, these are the sort of questions I know you love, where instead of just doing maths and coming up with an answer, you have to explain yourself. Yeah, I know you love them. Now, okay. Y is the most general form given by ax plus b. What would the reason for that be?
The degree has to be less than 2.
Exactly. Yeah. See, we're dividing by a quadratic. Therefore, we know the best it could be, or the biggest it could be, is a linear function. So a general linear function would be ax plus b. Excellent answer. Now, given that polynomial 4 is negative 5, show that remainder 4 is negative 5. There's our polynomial. We know our divisor is x plus 1, x minus 4, times the quotient, plus a remainder. Sub in 4. Oh, once again, the q4 will disappear because of my 4 minus 4. So polynomial 4 will be the same as remainder 4, and they've told me remainder 4 is negative 5. No, sorry, they've told me polynomial 4 is negative 5, so therefore remainder 4 is negative 5. Further, when it's divided by x plus 1, the remainder is 5. Let's find the actual remainder. So, remainder 4 is negative 5. We now know that. So 4a plus b, if we sub it in, because the remainder, there it is, we've said it's going to be ax plus b. So 4a plus b is negative 5. We know polynomial negative 1 will be 5 from our remainder theorem. So minus a plus b is equal to 5. Simultaneous equations. And we get a is negative 2. Now what's b? b is 3. So therefore, the remainder is minus 2x plus 3. All right. There we do. 4D.